So we're looking now at section 8.2, which is using vector methods to deal with the projectiles questions. Now, this is perhaps not too surprising because we know in projectiles questions we always think about moving horizontally, moving vertically. Horizontally, we apply speed equals distance over time, or S equals VT, as we usually call it in this part of the book in the projectiles chapter on the year 2 of the A-level course. Vertically, we have a constant acceleration going on, so we apply the Suvat equation. So we apply vertical and horizontal things separately, and that's exactly what you get in a vector, isn't it? You get the horizontal motion described in the first component and the vertical motion in the second component. So we can put those things together and deal with this in a vectors way. Now, if you've already done the vectors part of the pure book, you'll have seen these sorts of questions as well, okay? So that's the idea. We're going to deal with the same methods, but we're going to put them all in one vector. Let's have a look at the example, and hopefully you'll get the idea. Here we've got a ball struck from a racket at point A, which is 20 J meters vertically relative to a fixed origin. In other words, we're starting 20 meters high, and the origin is down here. We hit the thing off the top of this cliff or this wall or whatever it is. Quite a high wall if it's 20 meters, isn't it? But there we go. And it goes that way. We start with the speed of 5, 8, and I'm going to go for column vectors. If you prefer to write that as 5a plus hj, that is obviously fine. After being struck, the ball travels freely under gravity until it strikes to the ground. We're calling this point A, we're calling this point here B. So, find the speed of the ball 1.5 seconds after being struck. So what do we have? We have u, v, a, s, and t. U is my initial velocity, which is 5, 8. V is the final velocity, which I'm trying to find. If I want to find the speed, I need the velocity, and then I find the magnitude of the velocity vector. Acceleration, I'll come back to in a second. Don't care about that one for the moment, and we are, what are we? 1.5 seconds is my time. Now, acceleration. Horizontally, this thing is not accelerating. Vertically, it's accelerating downwards at a speed of 9.8. Now, if you're writing that as i's and j's, then the acceleration is minus 9.8 j, okay? Now, again, I prefer the column vectors, so I need a 0 in my x component place. Now, the other thing to spot here, which is perhaps not a major point, but I think it's an important one because for some people this will make a difference to the way you do these questions. Previously, whenever we've had a Suvat equation going up and down, so the AS kind or the A2 kind, the vertical motion of the A2 sorts of questions, we've been able to pick which direction is up and which direction is down. Now, some people always pick up as a positive direction. Sorry, we've been able to pick which direction is positive, up or down, right? Up is always up and down is always down. We don't get to choose that. So, if you always pick positive as upwards, then the acceleration has always been negative, always minus 9.8. But if we have a question, for example, where we just have an object and we're just dropping it, or we're hitting an object horizontally and it's just falling downwards, then for the vertical motion, for a lot of people, they will choose positive as the downwards direction because all the motion's happening downwards. In this case, we have a vector system where upwards has to be positive because that's the way our vectors work, right? And if we had any doubt about that, they've given us in the question that 8 is in the upwards y direction. So that means the acceleration has to be acting downwards. If all the motion is downwards, we still have to have downwards as negative because we're dealing with vectors. Shouldn't be too much of a shift for anybody, but it's just a point that's worth pointing out because that's the difference between this and some other questions perhaps. Okay, so where are we? We have these things, and that means that we're going to use the formula which is familiar to us from section 8.1, v equals u plus at, and obviously from earlier in the course as well. So the final velocity is 5.8 plus the acceleration, which is 0 minus 9.8 times 1.5. So 0 minus 9.8 times 1.5. And of course the 0 times 1.5 is still 0. So there's my final velocity if I work that out, and I need the magnitude of it to have the acceleration, okay? Find the expression for the position vector of r of the ball relative to O at time t seconds. So if I want the position vector, then I get u, v, a, s, and t again. Now, this is where the question is a little bit more complicated. Let's just put the usual things in. 0 minus 9.8. The time taken is t seconds. Now, we don't care about the velocity. We want to find the displacement. So that's what we're trying to find. Now, if I use r equals ut plus 1/2 at squared, that's going to get me, well, first of all, if we substitute all this stuff in and simplify it, then we're going to get 5/8 times t minus 4.9 times, plus 0 minus 4.9 times t squared, okay? So that's going to give me 5t, 8 minus 4.9 t squared. Sorry, I'll shift this up, here we go. So all we've done so far is take u, v, a, s and t, we substitute into this equation, and we get this. Now that thing there is the displacement from this point here. So let's say I'm here on the curve. What I've just got there is a vector which tells me the position vector, the position of this point, the displacement of this point from here. And it tells it me as a vector in terms of time, okay? Now, what it wants in the question is the displacement from the origin here. So the vector that we want is this vector here, from the origin to here. So how do we deal with that? Well, first of all, we make sure we've got a diagram drawn, because now we've got a diagram drawn, it's not too difficult to see. This vector here that I want is this vector plus this vector. So how do I get that? Well, I've just got to add on this starting vector. That's 20 meters upwards, so that's just a vector of 20j, or 20 in the vertical direction. So 5t, 28 minus 4.9 t squared. And that there is the vector that I want. That vector is 20j plus that. Okay, 20 vertically plus that thing. That thing there is the displacement measured from my starting point. And that's the other thing. That's the only other thing we've got to remember, is that this, in this equation, this vector is the displacement from where you start. So if your origin is somewhere different, we have to adjust in that way. If it's at all unclear, make sure you've got a diagram, and hopefully that will help. The distance from O to B, well, the distance from O to B is when the vertical displacement is 0. Okay, the vertical displacement is 0. B is at the same height as O. So I'll take this equation here. I take the vertical component of it and I put it equal to 0. And when we do that, oh dear, sorry, I've just realised there should be a t in here, shouldn't there? So that should be, what's that? 20 plus 8t minus 4.9 t squared. Sorry about that. I'm going to be too lazy to go back and fix that. Hopefully that hasn't been too confusing. Even so, same idea. Vertical displacement is going to be equal to 0. We put that equal to 0. We solve for t, and we'll find two different t values. If you look in the blue box, you see that one of them is positive, one of them is negative. And what does it ask for? The distance OB. We need the horizontal distance when at the point when the vertical distance is 0. So take that t value, substitute it into this x component, and that will give us, it turns out in this case, about 15 meters is that distance there. Now, if you just keep that in mind as though it were one of the questions from the projectiles chapter, that's exactly what we do. If we've got the vertical displacement in terms of time, we say, well, when is the vertical displacement 0? Take the answer for time and put that into the horizontal speed equals distance over time equation. Okay, that's the end of section 8.2. Hope that helps.